Hi everyone! The next shortcut on our list is the quotient rule. So we're going to work on the quotient rule, and we are going to start by finding out what the shortcut is, but I'm going to approach that in a little bit different way. So once again, I won't test you on actually proving the shortcut, but please watch so that you can see where these come from. And this one should be interesting because we're not going to start with difference quotients the way we have. You can prove the quotient rule that way, and if you're interested, let me know. I can find you a video with that. But I'm going to start to introduce a new way that we can build up some of our shortcuts that we'll use again after this as well. So we're just going to start by naming a function q of x for quotient, f of x over g of x. So we're trying to find the derivative of f of x over g of x, and I've just renamed that q, and our goal is to find q prime of x. So my first step here is going to be rearranging a little bit. I'm actually going to solve this for f of x, and I can say that f of x is equal to g of x times q of x. And the reason this is helpful is because while we don't know the quotient rule yet, we do know the product rule. So we know how to find f prime of x. F prime of x is the second, q, times the derivative of the first, g prime, plus the first, g, times the derivative of the second, q prime. And now remember, our goal was to find q prime of x, so I can solve that. This is not a terribly hard equation to solve. So I'm going to go ahead and subtract off q times g of x. So I have f prime of x minus q of x times g prime of x, and that's equal to g of x times q prime of x. And then I can divide both sides by q, and I'm going to flip-flop sides here as well. So I'm going to say q of x, q prime of x equals, and then we'll have that f prime of x minus q of x times g prime of x all over g of x. And this is pretty good. My one problem is that q wasn't part of the original question. The original question is what's the derivative of f of x over g of x. I just made that up to represent what I'm looking for. So I want to go a couple more steps. I want to plug back in for q of x. So I'll have an f of x over g of x. And then I'm really close, but I don't love the fractions in fractions. So I'm going to multiply top and bottom by g of x to clear those fractions in fractions. And what I find is that the derivative of f of x over g of x, which is what I actually started with, is equal to g times f prime minus, when I distribute here, the g's just cancel out, so I'll get f times g prime, and then on the bottom I just have g of x squared. And this is your quotient rule. So again, search YouTube if you want ideas for how to memorize this. I'll tell you how I say it, and I'll even tell you one that I hear a lot that's just a little bit different than how I say it. So the way I say it in my head is this is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That's how I keep track for myself of what goes where. The other one that I hear a lot is that people call g of x low and f of x high, and they'll say low d high minus high d low over low squared. And that one I know can come in a song version. At the end they say over low squared and away we go. So look those up if you're interested. One nice thing that you can notice here is that the top looks very similar to the product rule. The only difference is that there's a minus sign in it. So if that helps you, it is the same setup in the top just with a minus in the middle. The minus does mean that the order is not flexible here. It is very important that it's FG prime that comes after the minus. If you reverse the order, your quotient rule will be wrong. So do be careful about order. Okay, so that's your quotient rule. Please memorize it. As promised, I'm going to go through and show you how you would get the shortcuts for the remaining trig functions, given that we know the shortcuts for sine and cosine. So if you've got those memorized and you're not really interested where they come from, now you have permission to skip. If you are interested, I wrote that kind of in my way, but let's see if we can fit that here. So the way we would approach this is we'd say, tangent is sine x over cosine x. So if we apply the quotient rule, we get the bottom, the derivative of the top, the derivative of sine x is cosine x, and then we get minus the top, sine x. The derivative of the bottom, derivative of cosine, is minus sine, so that actually becomes a plus. And then we're supposed to divide by the bottom squared, so cosine squared x. Notice the top is actually cosine squared x plus sine squared x, and I really hope that stands out as an important thing that you're supposed to recognize. Sine squared plus cosine squared is always equal to 1. That's our Pythagorean identity. So I get 1 over cosine squared x, or secant squared x, whichever way you want to write that one. So there's the tangent shortcut. Very similarly, in fact, if you're following along, you might want to pause and run through this one yourself really quickly. If we want to do cotangent, we could do cosine over sine, and there are other ways to get this as well, but this is the one I'm going to do. So we get the bottom times the derivative of the top. So the derivative of cosine is minus sine, and then minus the top, cosine, times the derivative of the bottom, the derivative of sine is cosine, over sine squared x. And what happens with this one is we have a negative sine squared x minus cosine squared x. The Pythagorean identity doesn't have the minuses, but you can factor that out, sine squared plus cosine squared. So if you factor out the -1, in parentheses you get sine squared plus cosine squared, which is equal to 1. So we just have an extra negative floating around. We get -1 over sine squared x, which is an acceptable answer, but is otherwise known as negative cosecant squared x. So there are your two tangent and cotangent shortcuts. For secant and cosecant, the way I would rewrite those is using the reciprocal identities. So secant is 1 over cosine. And then again, you can use a quotient rule on this. You can also use a chain rule on this, which we'll learn next. So if you're interested, you can think about that when we get there as well. So here we get the bottom, cosine x, times the derivative of the top. The derivative of 1 is 0, so that's actually just going to wipe out, minus the top times the derivative of the bottom. Derivative of cosine is minus sine, so this will become a plus sine x. And all that is over cosine squared x. So I end up with sine x over cosine squared x. And it might not be immediately obvious that that is what we were expecting to get, so I'm going to split this fraction up. I'm going to say I have a 1 over cosine x times a sine x over cosine x. And that's definitely equal to what I started with. I could just multiply straight across and I'd get sine on the top and cosine squared on the bottom. And now I think it's a little bit easier to see. 1 over cosine x is secant x, and sine x over cosine x is tangent x. Okay, last one. So again, you just saw a really similar one. Try this one on your own if you're up for it. Cosecant is 1 over sine. So if we apply a quotient rule, we'll get the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is cosine x, all over sine squared x. So this is negative cosine x over sine squared x. And if I split that up again, I'll have a 1 over sine, and then a cosine x over sine x, which is negative cosecant x. 1 over sine is cosecant. And then cosine over sine is cotangent x. So once you've got sine and cosine shortcuts, you can really get all the other ones just using our basic shortcut rules as we build them up. All right, thanks for watching.